Brain-machine interface specifically maybe isn't a neuroscience discipline, it's an engineering discipline. Right? So like the mid 2000s is when engineers actually got involved, right? Like, so some of these sort of early neuroscience labs that were doing this, they did amazing stuff. I don't want to offend anybody, but there's this like treasure trove of stuff that just wasn't applied until, engineering labs sort of started taking brain machine interfaces seriously. And I'd also argue that like neural engineering as its own discipline wasn't a thing back then. It's really hard to just take a bunch of neuroscientists and electrical engineers and like try to get something that actually works. Now there's a ton of people that work right on that boundary. So I think that that's why it sort of accelerated recently. Like it may look like a neuroscience lab when you walk in, but we are discovering ways of building neural interfaces, right? So yeah, I mean, I think it is very pragmatic. I think it is really important. I mean, that even if you're not going to do the human research, that you have those conversations with the clinicians and like get a real sense of what you're going to be in for, and make sure you have a deep understanding of like, where this is all going and what has to happen.
I think everybody would have said that neuroscientists who are studying computation are spike obsessed, and nobody's going to do anything where you can't record spikes, right? But then, we have these optical reporters, calcium reporters, that are too slow to record spikes, but they have all kinds of other advantages like genetic tractability and so on, and targeting and lots of neurons at the same time. And suddenly everybody's using them. And now, of course, the technology's caught up and you can do those.
I think it's important not to overinterpret some of these decoding results, because to some extent it depends on the task complexity and the number of neurons you're recording from. I don't think it's a given that for all applications you won't need that information.
Yeah, no, I mean, I think that eventually sorting multiple units might be a thing. I mean, yes, at some level it has to be. In practice, though, like, so I mean, it's a 10x power reduction, right? Like, you want more crappy channels for BMI, than like a couple of perfect ones. Right. And I really think the neuroscientists, like they need the perfect ones. They need, multiple sites dedicated to seeing that neuron from, 360-degree angles and all that. And so I think it's different. So.
Well, but I would what the argument I was making was going even a little bit further, which is that, I mean, I don't disagree with you, Matt, but going in the other direction, if I could offer you 10, 50, 100, 500,000 neurons at the kind of precision that Cindy's talking about, and you could get that across lots of areas, researchers would use it. And they'd figure out ways where the questions they were asking were well tailored to that level of data capture, and they'd use it. But I do think that the kinds of things that happen in academia are very different from the kinds of things that happen in industry.
I think I've been in research for like going on 20 years now, and I don't think I really appreciated the difference fully between academia and industry until my research field got proper startups in it. So now I get it. And it's actually, it feels really empowering in the sense that like, in academia, we're shiny object chasers. And that is a super fun job. We are looking for like new nuggets of knowledge, and our job is to like plant a flag over it and say, hey, there's a new nugget over here, and just keep calling attention to anything new we discover. I agree. As Flip mentioned, that's very, very different than having, 40 people work on one thing and push in the same direction. In a lab, you can have 12 people that are, working on completely different visions and completely different directions. If everybody's looking in a slightly different place, you're more likely to find something, but you're never going to, finish a product like that. Like you're just, it's proof of concept and then you're done, and it goes somewhere else or it's done.
I love that this is a group that's not afraid to be controversial. And I want to start with Cindy. Where do you think people are wasting time and money? In neural engineering?
Oh, I don't want to be mean. So
you don't have to name labs. We won't cite anyone. But in general, what do you think are dead ends?
Okay. I do have to say, so I don't disagree with anything Flip said. I think there's a lot that can be had of like semi-invasive signals. I'm pretty sure EEG is farmed out, right? In terms of like real-time control. Now I want to like specify again, what they're good at is super controlled settings, repeated stuff. There's so many good neuroscientists in the world. There's still clinical applications, but real-time single trial EEG, like I don't think is a thing, right? It's hope. So not physics. Was that controversial enough? Was that good?
No, that doesn't bother me at all. I think the question you have to ask yourself is, what are you trying to achieve? There hasn't been a lot of clarity in the field sometimes about matching technology to application. And so I'm actually hard pressed. I love being a critic. It's one of the things I'm best at. And so I'm a little surprised that I'm hard pressed to come up right now with something that I think is just clearly the wrong approach, because I really think it depends on the application.
Yeah. All right, I got another one. I think it has to be the end of traditional ASICs, right? Like we're done. We have enough. Okay. Like, whereas if your ASIC is an LNA followed by like an ADC, and then you want to do machine learning on your ASIC for some reason, like that's I think that's pretty traditional at this point. It's farmed out, right? It should be commercial or nothing.
Okay.
So.
But you're not saying it's a bad approach. It's just saying it's not a good approach to be doing as an academic.
It's certainly a bad approach to be doing as an academic. I kind of thought the Neuralink system is over-designed. So, but I don't know that much about it.
That's getting pretty specific.
Yeah. No, I don't think you need like the front end amplifier. Like I'm a big fan of like the neural dust approach, right? Like if you can do that with one transistor, just like I think that the answer is closer to these minimalist systems that get you, one crappy signal. And then you just get a lot of them. So like, I think that, reconstructing, like by the time you have spent your power consumption on a whole front end amplifier, you are out of power. Like
I'm not sure
you don't have enough. Yeah.
I'm not sure that neural dust makes sense as a concept.
It doesn't, well, no, okay. So this is the shiny object also that I get to chase as an academic. That's like too crazy for you guys. Right. So I think there's a bunch of potential concepts. So I'm not saying that ultrasound.
Let's talk about neural dust. Let's take.
Yeah.
I'll take aim at something. Let's talk about neural dust. Let's talk about delivery. Getting it deep. You're either delivering it like a gene gun, ballistically, and that's crazy, or you're sprinkling it on top. In which case, what you've done is a really over-engineered ECOG grid. Why not just use an ECOG grid?
ECOG grid?
Well, so okay. So let me. Yeah. So I don't know. So this is, it's not completely unpublished, but yeah, no, I think that you can get up and close and personal with the neurons, and I think you can deliver power to thousands of motes, right? So, what we're proposing is an infrared powering scheme, something like a 200 by 200 micron chip that sits on the surface of the brain and a carbon fiber that goes deep. Right. And the fun of using carbon fibers compared to some of this other stuff is that it has a lot of penetrating power. Mm-hmm. So I can sharpen a carbon fiber and just drive it to cortical depths. Right. And so you can just push them in.
That's stretching the definition of neural dust. Really, you're talking about a penetrating microelectrode with a very small wireless kind of.
Yeah, it's got so neural dust by itself doesn't make sense. Your device needs extent so you can record. So how we're getting, it's a little like carbon fiber tail, right? On a piece of plastic. So yeah.
And I think at that point, whether it's wireless or wired, whether there's a single ASIC or there's a bunch of little modes, I think these are details. I don't think they actually address the fundamental questions, to be honest.
What's the fundamental question?
The thing
what are the limits? What are the limits, and where can you go? So you're describing one approach to interfacing with lots of penetrating electrodes, but I think there are other approaches, and it's not clear that the wireless aspect of that is necessarily the key innovation of what you're talking about.
Sure. And I think people have proposed all kinds of powering systems for neural dust, right? Like, and there's, and not all of them are impossible yet, right? Like some of them still have runway left.
Right.
Yeah. But in reality, that material challenge is kind of still unsolved. I would say if the thin film issue, if you can have a thin film that has really low water vapor penetration, can last for 10 years, I'm on board. I would take a neuropixel, I'd wafer thin it, and I'd make 10,000. I'd put 10,000 neuropixels in. But I think until that's a solved problem, you're going to be looking at platinum, iridium, carbon fibers.
Yeah. No, if I was going to write a science fiction series where like suddenly one new technology turned up and changed everything, it would be the magic coating.
Yeah.
Right. That suddenly lets you make, all of your medical devices can now be chip scale, right? Because you have the magic coating. And so it'd be great if we had it. I wonder if material science has been as fully engaged as they could be. Maybe it's out there somewhere. I don't know.
I was just going to say earlier, though, that in response to Cynthia, that, obviously that the coatings and longevity are an issue, but I don't think it's the only really hard technical problem. Delivery remains a hard problem. If you're going to be putting that many devices into the brain, you've still got to worry a little bit about blood-brain barrier. You've still got to worry about wires. You've still got to worry about processing and heat dissipation. So,
although for the scales we're looking at, I mean, we're comfortable with where the heat dissipation is right now. And I mean, partially due to Cindy, also Takashi Kozai's work, and you share common Paras Patel. All of the work with carbon fibers, I think, is really encouraging about the blood-brain barrier. If you get small enough, that data looks really good.
Yeah, well, so I was going to say, I mean, I think that I think there is a chance that you can get small enough and maintain enough penetrating capability that you can get in there without breaking blood vessels, right? And I'm also basing that on Nick Malash's lab at Stanford also, and I'm not sure. I think the delivery problem is much harder for soft devices. I'm not the devices may ultimately need to be soft for this, to be completely utterly biocompatible. I don't know. But maybe not. Maybe you can get, whether it's carbon or tungsten or something hard, platinum iridium, you can actually get pretty far below cellular dimensions and still get something into the brain. Right.
No, I agree. I totally agree. I was thinking about scaling up because you were talking about the science fiction. So I'm imagining going to 10,000.
But why can't I do that 10,000 times, right? If the first one doesn't break a blood vessel and I put them far enough apart, right? I mean, say I put them 200 microns apart, and if you're not breaking capillaries, you're not breaking capillaries, right?
The fact that you can put a few carbon electrodes without breaking a blood vessel is not convincing to me, because I want to see many hundred, many times. Yeah, many times.
Isn't that being done though, Matt?
Well, yeah, I mean, and maybe the counterpoint is also take the Utah array. The Utah array is, when it implants, pretty messy, to be honest. It causes a lot of disruption, but it's allowing people to move cursors, move robotic arms, decode handwriting, and it lasts for years. So, I mean, I think it's important not to get academic about this. You don't want to take the position that you can't disrupt the blood-brain barrier or you don't have a product.